Lie down and look up at a dark night sky. Look at the moon and the stars and the planets moving around you overhead. Look up at wonder at the majesty that is our universe. Our ancestors did this, and for a long time they pondered what kept the moon and the planets and the stars where they are. It took us a long time to get there, but undoubtedly now we know that gravity is the answer. Gravity, one of the four fundamental forces of nature. It permeates throughout the entire universe. Wherever there is matter, its pull can be felt. Yet, of the four fundamental forces, electromagnetism, the weak nuclear force, the strong nuclear force, and gravity, gravity is the weakest by far. So what is gravity, and how does it hold our whole universe together? Greek philosophers thought that the planets and stars were part of God's realm and followed a natural motion. Aristotle believed that objects have a natural tendency to move toward the center of the universe, which he believed to be in the middle of the Earth. In fact, it wasn't until the 1500s that the Polish polymath Nicholas Copernicus reasoned that the paths of the planets in the sky make much more sense if the Sun is at the center of the solar system. At that point, astronomers like Galileo and Brahe started to look for and found evidence that the Earth and other planets actually did revolve around the Sun. Later, Kepler showed that the planets actually moved in elliptical orbits, not a circle. The question then was, what was this amazing force that kept everything around the Sun? Then, in 1687, Sir Isaac Newton, in his famous treatise Philosophiae Naturalis Principia Mathematica, gave us what is now called Newton's law of universal gravitation. The story goes that Isaac was sitting under this tree at his home, Walthorpe Manor, in Lincolnshire. It was late summer, just heading into autumn in 1666, and the first of the autumn leaves were caressing the ground. The then 24-year-old Newton was looking out over the garden when an apple fell from the tree and landed on the ground in front of him. This seminal moment sparked the fire of revelation in the young scientist's mind, and over the next 21 years he would, through experimentation and mathematical genius, come to his amazing formula which gave us a deeper understanding of gravity. Force due to gravity equals the mass of the first object times the mass of the second object, divided by the square of the distance between them, all multiplied by the gravitational constant. Newton's ideas on gravity were a revelation. Newton showed that gravity was a force created between any two objects with mass, and the larger and closer the objects, the more gravitational force there was between them. Now we had a reason why objects orbited the Sun and why moons orbited planets. The universe was slowly giving up its secrets. In 1798, British physicist Henry Cavendish conducted one of the world's first high-precision experiments to try and precisely determine the value of G, the gravitational constant. Cavendish built what's known as a torsion balance, attaching two small lead balls to the ends of a beam suspended horizontally by a thin wire. Near each of the small balls he placed a large spherical lead weight. The small lead balls were gravitationally attracted to the heavy lead weights, causing the wire to twist just a tiny bit and allowing him to calculate G. Cavendish's precision was outstanding. His estimation for G was only 1% from its modern day accepted value of 6.0 0.67408 times 10 to the negative 11 meters cubed, kilograms to the negative 1, and seconds to the negative 2. The next great advancement in our understanding of gravity came in a new theory that originally had little to say about gravity. The special theory of relativity was the brainchild of a young and brilliant theoretical physicist named Albert Einstein. Published in 1905, the theory reconciled conflicts between Maxwell's equations, the laws of electricity and magnetism, and the laws of Newtonian mechanics by introducing changes to the laws of mechanics. While to us, moving at ordinary and everyday speeds, these changes are not really apparent. At high speeds, i.e. velocities that approach the speed of light, these differences become more and more apparent. Einstein's theory counterintuitively predicts that time and space are no longer fixed but change relative to one's motion through them. So a clock carried by a moving body would appear to slow down, and the body itself would contract in its direction of motion. The paper also removed the need for the luminiferous ether, the postulated medium for the propagation of light, which had failed to be detected by Michelson and Morley in their 1887 experiment and subsequent follow-ups. In 1908, Hermann Minkowski reinterpreted special relativity in geometric terms as a theory of space-time. Einstein adopted Minkowski's formula in his 1915 General Theory of Relativity, and for the first time we had a real mechanism for how gravity worked. Mass and energy warped space-time. The more mass or energy you had concentrated in a location, the more space-time warped. And objects in these warped areas of space-time followed straight-line paths that followed this curvature. So the motion of stars and planets, and the force that kept us securely on the Earth's surface, were all just manifestations of the same effect of curvature of space-time. In the time since Einstein's General Theory of Relativity was published, the theory has been confirmed over and over again, from calculations of the perihelion of Mercury, the prediction of black holes, and the detection of gravitational waves. General relativity is one of the most supported theories of modern science. So what is gravity? Gravity is the distortion of space-time caused by the concentration of matter and/or energy in a particular location. Gravity keeps the planets in motion, the galaxy turning, and the universe together. But mostly, gravity keeps our feet on the ground and gives us this wonderful world that we call home.